This is Hunter Anderson, and my physics partner behind the camera right now, Emily Harrington. We're going to show you how to use a sounding today for forecasting 2 out of the 4 main characteristics that relate to physics in forecasting severe weather. Now, the 4 main characteristics and parameters that we use go by the acronym called SLIM. S is for shear, L is for lift, I is for instability, and M is for moisture. Now, a little physics pun here. We're only going to be using the SI, get it, SI units? We're going to be only using the SI here for the sounding. We're going to be showing wind shear vectors, how to transfer them over into a hodograph, as well as measurement of instability or CAPE in the atmosphere, which relates to thermodynamics.
So following what Hunter said, we're going to use the skew-T diagram to look at a sounding from April 27th of 2011. This is your temperature sounding, this black line that goes all the way up to the top of the skew-T, and this is your temperature dew point sounding, which also goes to the top of the skew-T. So in order to find out what our CAPE and SIN are, which I'll talk about a little bit later, we need to first establish a few things from the skew-T. These dash marks right here are 50 millibar increments of height in pressure, which the pressure is millibars, or you can also say hectopascals. These are 50 millibars, so this is 1,000, 950, 900, 850, and so on. So the higher you get up, the lower the millibars go. Now, to determine the LCL, or lifted condensation level, we look at the temperature at the bottom of the sounding at 1,000 millibars and follow the dry adiabatic line up a decent ways, about to 850 millibars. Then you also use the temperature dew point and follow that up the saturation mixing ratio line about to 850 as well, until these 2 lines connect. When these 2 lines meet, that is the LCL, which we have marked right here. LCL is the base of your clouds as well. Now, using this information, we can determine the instability of a sounding. So, looking at SIN, which is convective inhibition, this is what we need to overcome in order to gain a lot of instability in the atmosphere. So as you can see, this is a decent amount of SIN, but it's still easy to be overcome. Then CAPE is convective available potential energy. So CAPE, we have 2 areas of CAPE on this skew-T, this little red part and this larger red part. These 2 areas are where you have a lot of instability in the atmosphere.
Alright, so Emily just mentioned the I acronym for SLIM, which was instability. Now we're going to talk about the S, which is shear. So as Emily mentioned before, these increments right here are your pressure in millibars. So right here is 1,000, right here is 950, right here is 900, 850, 800, so on. We only went up to 400 just because we don't really need to go much higher for this example. So what we're looking at now is shear, which is change of wind direction as well as the change in height with your wind speed. So in order to understand how to read wind barbs, first off, we look at how fast the winds are going, which are long lines right here. This indicates 10 knots. So right here we have 10, another 10, so that's 20 right here. And then we have a short one right here, which is 5. It's half the length of the long one. So right here we have 10 knots near 1,000 millibars, which is right near the surface, and then up here at 950 we have 25 knots. So an obvious increase of wind speed and shear as you go higher. The flag that you see here at the 850, as well as up here near 700 and 600s, the flag's 50. It's 50 knots. So right here is 55. You have a flag and a short stick, and then Up here you have a flag and a long and a short stick. So right here, this is 65 knots. So in order to understand the wind direction, we like to pretend that we have a compass rose here. So right now, based off the wind, top of the page is north, bottom of the page is south, right page is east, and the left side of the page is west. So let's take a look now at the way the wind is going. So we like to pretend that this is like a bow and arrow. You have your feathers here on one side, and then this is the way that the arrow's pointing. So this arrow right here, it's pointing northeast, as well as this, and basically all of these. Most of these arrows are all pointing to the northeast. So that means the wind's coming from the southwest. So that's why we say we have a southwest wind. We have a wind coming from the southwest going to the northeast at 10 knots, 25 knots, 40 knots, 50 knots, and so on. Now the next part here is how we transfer these wind barbs into a hodograph, which you take the wind vectors from your wind profiles and transfer them into a graph. Alright, this next part is a little tricky, and this is what trips most people up. So in order to measure the wind direction, we do our north, east, south, west. So we also use degrees from 0 to 360. So we pretend that north is 0 degrees, east is 90, south is 180, west is 270. So when you say you have a wind coming from 190 degrees, that means you have a south-southwesterly wind, which is what this wind barb right here is indicating. 190 degrees between 270 and 180, and really close to 180. It's only 10 more degrees higher, so it's going to be closer towards south than west. So that's what this wind barb is indicating here. Now in order to transfer this onto a hodograph, we have to switch the degrees around. With that being said, north is going to be 180 degrees, south is going to be 0 degrees, east is 270, west is 90. So instead of going like this, we're starting south and we're going like that. So that's what trips most people up into creating a hodograph. A hodograph is basically a graph using polar coordinates. So it's all in a circle here, it's all circular. So start in the middle, that's 0 knots, 10 knots on the first ring, second ring's 20 knots, 30, 40, 50 knots. In order to transfer these wind barbs onto here, see this first one here, we have 10 knots. 10 knots at about 190 degrees. So if we have to pretend that this is 180 degrees up here, as depicted on this right here, 0 degrees down here, 270 over here, and 90 over here. So if we have a 190 degree wind at 10 knots, this is the center right here. 10 knots is right here, and this is 180 right here, 270. So 190 is about right here. So this is where we put the first plot. Second wind barb here at the next 50 millibars up is 25 knots, and that is about 195 to 205, 210 degrees maybe. So we put that slightly a little more to the right as it's closer to the 270 degree previous to the first plot. And since it's 25 knots, we put it right between the 20 knot and the 30 knot ring. So that's how we get this plot right there. And we keep doing that all the way up. So this one here, we have 55, although it's outside our ring here. We can infer that it's just going to estimate distance from the rings. That's going to be up here. So if we have a 55 knot here at, what is that, 650, and it's at about, you'd say 225, 220 degrees, we put that a little more this way, as it's not as close to the 180 degree mark or the 270, so it's going to be right in the middle. So, and we have, since we have 4 55 degree knot winds, we have 4 dots pretty much up here simultaneous next to each other. So we just basically connect the dots when you're done, and you're gonna have a crazy looking photograph that will end up looking like this when it's all said and done. And obviously this is a rough sketch, but that is the general shape of the photograph in Alabama on April 27, 2011.